Hi, this is the first video for the lesson More Than Meets the Eye, Transformations of Quadratic Functions, and the topic titled Introduction to Quadratic Functions. This video will focus on translations and reflections of quadratic functions. So let's dig in. So as we've been studying transformation form with linear or exponential absolute value prior to quadratics, we are using the same form, but now we're going to be working with what if we have the function we're transforming is quadratic. So you might recall that A and D values were happening outside the function, so those were vertical transformations, and the B and the C values were happening inside the function, so those were horizontal transformations. So we're going to start off with vertical translations. So these are actually our D values in our transformation form. So what if I wanted to either add 4 or subtract 4 from the basic function g of x equals x squared? What effect would that have on my graph and in my coordinate notation rules? So let's take a look at that graphically. So if I have x squared, when I'm adding 4 to the function, that produces a vertical shift up 4 units. If I wanted to rewrite that in terms of x, instead of saying gx plus 4, that would take my basic function and I'm adding 4, so that's x squared plus 4. So that produces c of x, and I can see it lands on top of that transform function, therefore they're equivalent. So what if I wanted to subtract 4? So you might be going, well, if plus 4 was shifting up 4 units, and this is a vertical translation, this should shift down 4 units, and it does. And so if I wanted to rewrite that in terms of my function x squared, I could substitute that in for g of x and get the function x squared minus 4, or d of x equals x squared minus 4. And you can see it does land on top, so therefore they are equivalent. So what does that look like in a table of values? So if you notice, c of x was when we took our function and we added 4. If you look, the x values stayed the same, but look at our y values. So the point negative 416 mapped to negative 420 and so forth. And when you look at the mapping, you can see that the x values stayed the same, but our y values actually increased by 4. And that produces this coordinate rule here for this particular function. X stayed the same, we're adding 4, and really what that means is that we're just adding the d value, whatever that is, to y, whether it's positive or negative. So that would hold up here when we have g of x minus 4. If you notice, my y values are all decreasing by 4. So that produced this coordinate rule, and this holds up. When we add d, if d is negative 4, we're subtracting 4 from y. So horizontal translations is when I am going to, I'm going to move here, add 4, subtract 4 from inside the argument. Let's see what happens. So I'm going to move over here to my horizontal translations. So when I add 4 inside the argument, you might go, oh, plus 4, positive, we're going to shift right 4. But actually, remember, this is x minus c, so x minus a negative 4 produces plus 4. So I'm actually shifting left 4 units. So I can rewrite that in terms of x squared, so that would be x plus 4, that quantity squared, and you can see it produces an equivalent function. So x minus 4, that's x minus c. Our c value is a positive 4. So this produces the shift right of 4 units. And I can rewrite that as x minus 4 squared, and that produces the same function. Okay, so our rules are here for us. We should be, oops, I'm going to do it this way, just be adding that c value, whether it's positive or negative, to our x. So that would mean if we're subtracting or adding there. So let's look at a table of values to verify that. So if you notice here, this was first when j of x is when we had g of x plus 4. Okay, so if you notice, negative 416 is, we see negative 40, and you see negative 39. Well, wait a second. I want you to pay attention to this whole set of the y values, 16, 9, 4, 1, 0, 1, 4, 9, 16. So if you take a look, this sounds a lot like it, but we're just missing our top half. So if I expand my table of values, you can see that my y values actually didn't change. Just what x value that they correspond with changed. So really, when I look at that, my y values didn't change. So we need to investigate, well, what was happening to my x values? So negative 416 is actually now mapping to negative 8, 16. And negative 3, 9 is now mapping to negative 7, 9. And if I do this at 0, 0, this might seem a little bit more obvious. That mapped to negative 4, 0. So my y values stayed the same, but my x values are what actually decreased by 4. Does that make sense? So that is how I get this rule here. And if you remember, my c value here is actually x minus a negative 4. And remember, if we're talking about x minus c, it means c is negative 4. So my x values actually decrease by 4. If I lay down the table of values and kind of match them up like what I did here, it might be a little easier to see, because remember, our table of values, x are side to side. These were vertical tables. So if I kind of lay these down, you can kind of see where you have a shift in our graph left 4. So it's kind of easier to see that way. Okay, so when I am now have x minus 4 inside the argument, what's happening in my table of values? And so again, you're going, wait a second, where are these set here? We can see half of it, but if we expand it, we now see it fully there. So where do they map to? Notice my y values really are not changing, just what x value they correspond with does. So I can also investigate that. And I'll just do a couple here. Negative 4, 16 becomes 0, 16. Negative 3, 9 now becomes 1, 9. And if I did 0, 0, that now becomes 4, 0. So again, my x values are the ones that are changing, not my y values, and I can see that they've all increased by 4. So that's how we get our rule here. Okay, now reflections. So now I'm multiplying outside the function by negative 1 and inside the function by negative 1. So graphically, what is happening? So if I move over to my graph of reflections, when I multiply by negative 1 outside the function, I'm reflecting my graph across the x-axis. So coming its opposite, just flipped over the x-axis, okay, from where it started. So now, what if I multiply inside the argument by negative 1? Well, it looks like nothing happened. It's the same graph. Well, actually, it is reflecting across the y-axis. But because our graph is already symmetric about the y-axis, it's just reflecting onto itself. So if I take any point, I'm now reflecting it across, and it just looks like it's the same point, but it actually isn't. So the best way to see this is to actually transform a function that is not symmetric about the y-axis. So let's say we start with this function, and if I multiply by negative 1, it reflects across the x-axis, outside the argument, and inside the argument, it reflects across the y-axis. So now that I've learned that, I can see my coordinate rules here. Is that, notice when I had multiplied by negative 1 outside, my y values all became their opposite. It's hard to tell in this table of values when it's symmetric about the x-axis. It looks like nothing changed, but actually what is happening is that my x values are becoming their opposites. Okay, so if we put this all together and we transform a function that is not the basic function, f of x or g of x equals x squared. Let's say we have this function in general form. It starts off by looking like this. When I now transform this function by adding 4, that should shift my graph up 4 units. So vertical translation up 4. F of x minus 4 should be a vertical translation down 4 units, which it is. F of x plus 4, that should be a horizontal translation. Remember, that's x minus negative 4, so that should be left 4. So it is. And f of x minus 4, that c is positive 4, that should be shifting right 4, which it does. When I multiply outside the function by negative 1, it should reflect across the x-axis, which it does. And lastly, inside the argument, we're multiplying by negative 1, and that should shift across the y-axis.